All right, let's dive right into this explainer and completely demystify the physical and logical infrastructure of the internet. For so many of us, the web just feels like magic in the sky, right? A mysterious cloud that somehow delivers streaming video and emails on demand. But today, we're going to break that illusion. We're going to transform that abstract idea into a very tangible, physical reality.
We're taking a micro to macro journey today. We'll start small with local networks and switches, move on to routers in the outside world, explore the network of networks, unpack WANs, VPNs, and security, look at request response and streaming, and then finally scale all the way up to the ISP hierarchy. Okay, Section 1, Local Networks and Switches. This is the absolute foundation of connectivity.
Let's start with the smallest possible network. Imagine a few computers in an office that just need to share some files and talk to each other. To do this, they first need to be grouped together into what we call a local area network, or a LAN. A LAN connects devices in a restricted physical location. Think of your house, or maybe a single office floor. You literally cannot create a LAN between a computer in the US and one in Russia. And at the absolute center of this local setup is a physical device. You've probably seen one sitting in a messy closet somewhere called a switch.
Now, the physical reality of these connections is super strict. Switches don't work with wireless signals. They physically require cables to link computers together. In a local office network, you're usually using standard copper cables like Cat5 or Cat6. They're cheap and perfect for short distances. But when you need to send data across the globe, that is where fiber optic cables come in. They transmit data as literal pulses of light at just mind-blowing speeds over massive distances. Moving right along to Section 2, Routers and the Outside World. Basically, finding the exit door.
So you might be wondering, how do we get those isolated local computers to actually talk to the rest of the world? Up to now, our switch just lets computers in the same room gossip with each other. But if one of those computers wants to, say, load a web page, the switch is totally useless on its own. Remember, a switch creates the LAN, but a router is your doorway to the outside world. It connects your distinct local network to other distinct networks, most notably the global internet. Without a router, your local network is completely cut off.
Which brings us to Section 3, the network of networks. We are zooming all the way out to the globe now.
Let's explore why the internet isn't just one giant router sitting in the exact middle of the Earth. I mean, imagine if it was just one massive router handling every single connection on the planet. If that one machine broke, the entire world would crash instantly. Instead, thousands of routers distributed globally manage the traffic. This distributed structure does three things. It prevents a single point of failure, it distributes the immense global traffic for efficient load balancing, and it completely avoids an impossible continent-spanning global cable mess.
To give you a real sense of physical scale on this global network, let me throw a crazy number at you. 468. That is the exact number of submarine fiber optic cables laid deep underwater right now that handle a staggering 99% of all international internet communication. When you send an email overseas, it is almost certainly traveling under the ocean.
And some of these fragile underwater cables are incredibly long. We're talking up to 20,000 kilometers, stretching across the dark ocean floor. Because they're physical objects, they are surprisingly vulnerable. If a ship's anchor accidentally drags across the seafloor and cuts one, or, get this, like an incredible incident in 2007 when sea pirates literally stole 11 kilometers of cable to sell as scrap metal, entire continents can experience massive internet outages in an instant.
So with all those public cables out there, carrying our data through pirate-infested waters and across thousands of different public routers, it begs the question, is it actually safe to send a highly confidential company file across the globe?
Section 4, WANs, VPNs, and security. Let's talk about protecting your packets. The answer to that security question is pretty complicated. And that's exactly why companies use wide area networks, or WANs, to connect different, distant offices securely. Now, setting up a completely private, physical cable between an office in New York and an office in London is, well, impossibly expensive for most businesses. So companies often use a VPN, a virtual private network. A VPN creates a secure virtual tunnel right through the chaotic public internet, acting exactly as if those two distant offices were connected directly.
Let's break this down with a really great analogy. Think of the public internet as a postman, and your packet of data is a letter you're sending. If you hand the postman a bare letter, they can easily read it. VPN tunneling is like putting that letter inside a sealed envelope. It hides the data inside that virtual tunnel. But what if the postman opens the envelope anyway? Well, that's where encryption comes in. Encryption writes your letter in a complex secret code.
So even if someone intercepts your data, just in case the postman peeks, it just looks like total gibberish.
All right, Section 5, Request, Response, and Streaming. Let's look at how websites actually load.
Let's see how all this builds into an everyday action, like clicking a video course online or Googling a quick question. When you click a video, your computer doesn't just magically receive the footage. It generates what's called a request packet. That packet is sent from your computer through your local switch, out your router, passed over to your internet service provider, and then routed across the world until it finally hits the target website's powerful computer, which is known as a server. Once the server gets that request, it formulates a response. But it doesn't just chuck a massive 1-hour video file at you all at once. The server breaks the video data down into much smaller packets and sends it back to you piece by piece. We call this streaming. This is exactly why you don't have to wait an entire hour for a file to download before you can press play. Your computer just processes the incoming packets in real time as they arrive.
And that brings us to our final section, the ISP hierarchy. Who actually runs the cables?
We've talked a lot about packets traveling across the internet, but who actually owns and manages all those global cables and routers shuttling these packets around? Well, the physical infrastructure is managed by a strict hierarchy of internet service providers, or ISPs. It starts locally. Your neighborhood local ISP manages your first point of connection. But they can't reach across the ocean, so they pass traffic up to a regional ISP, which handles city or countrywide networks. Finally, at the very top, we have the massive global ISPs. They manage the underwater fiber optic cables and continent-spanning systems, forming what we call the internet backbone.
Interestingly enough, there is a fascinating loophole in that hierarchy. Huge tech companies like Google use a technique called peering because they want their services to be lightning fast. Instead of sending their data through the slow public hierarchy of global and regional ISPs, they just pay to connect their massive servers directly to your local ISP. They bypass the global public traffic completely, and that is exactly why your YouTube videos tend to load flawlessly and securely.
So bringing it all together, the bookish definition you might hear in computer science classes is absolutely 100% true. The internet really is just the network of networks. It isn't a single nebulous cloud hovering above us. It's just millions of small local networks physically stitched together by an incredibly intricate web of routers, switches, and cables.
It's truly mind-blowing to think that this robust global brain, which powers our modern lives in mere milliseconds, relies entirely on millions of miles of physical, fragile cables buried beneath our streets and across the dark ocean floors. Which leaves me with this final question for you to ponder. As our hunger for data grows exponentially every single year, what happens when we literally just run out of room on the ocean floor to lay down these fragile lifelines? Thanks for joining me on this explainer. Keep learning, and I'll catch you next time.